have one more section to deal with. Oh, Jason's just arrived. And we're going to look at applications. And we're going to look at essentially three things. We're going to look at how do you find a Taylor series, Tn of x are called. Look at how good a fit is a Taylor series to a function, and how to estimate the maximum error in using Tn of x as an approximation to fx. And in case I forget, because it just came to me, the solution to question 6 from the test is in Canvas as a PDF. And it takes about 6 lines. And if you didn't overthink it, it's actually not that bad. I know a lot of you, pretty much every single person had trouble with it, but a lot of you are not quite finished grading, but a lot of the ones, you were in the right track, so you definitely got most of the points. So it's not like you lost a whole chunk of points. So have a look at that to check it over. Sometime this evening, you'll be getting your grades sent to you through Canvas email. So whatever your Canvas email is. Well, it won't be Canvas email. God, what will it be? It'll be whatever email I have on file with you, which doesn't always end up being Canvas. Okay, so focus back on this. What's a Taylor series? Well, we know what they are. That's a Taylor series. And you take a function and you find its derivative at a, you multiply it by whatever x take away a raised to the power is, and you do k factorial. Well, there's a particular version of Taylor series called Tn of x. For instance, if I wanted to find T3 of x, it would be the value of the function at a, the first derivative, the second derivative, and lastly the third derivative. Now notice that T3 means you go as far as the third derivative. And if you count these up, do you notice that there's 4 terms, even though it's called T3 of x? So it's not the entire Taylor series, you know, the one that goes to infinity, you know, the infinite polynomial. It's just, in this case, what, the first 4 terms, T3 of x. So far, so good? Now, to give you an example of what that might look like, suppose we take a function f of x. I want to pick a really easy one, sine x. And we're going to center this guy at pi over 4. And the question asked to find T3 of x. Okay, so how would I approach that question? This is what I would do. I'd find the first derivative. I'd find the second derivative. And I'd find the third derivative. And I know that that's as far as I need to go because T3 of x uses up to and including the third derivative, right? Now, for each one of these guys, I would then find the value of the function at a. So in this case, the value of the function would be the sine of pi upon 4. And I'm picking one that's got nice numbers, root 2 over 2. This one would also be root 2 over 2. This would be negative root 2 over 2. And this one here would also be negative root 2 over 2. So these are the first, second, third, and so on derivative. And then I put the package together. Right, it's the value of the function. So it's essentially, well, I'll put this line in. I wouldn't normally do this, but I'll put it in. It's going to be the value of the function at root 2 over 2 plus the first derivative, x minus a pi upon 4 over 1 factorial. The second derivative, and why am I doing that? I apologize, pi upon 4. I was putting the value there. That comes later. And the last one is the third derivative at pi upon 4. X minus pi upon 4 cubed over 3 factorial. Now I'll put all those root 2's in. This guy here is root 2 over 2. This derivative is root 2 over 2 x minus pi upon 4 over 1 factorial. This fella also happens to be that guy, but a negative. It's going to be x minus pi upon 4 squared over 2 factorial, which is 2. And then you get the last one, which is this fella. And by the way, 3 factorial is 6. So I'm trying to make it look a little bit prettier. I got this guy. I got that guy. That guy makes this negative. So that's what the next term looks like. That's worth 6. That's 2. That gives you 12. And that's what we call T3 of x. So that particular one, would you agree it's more time consuming than anything? It's not that the process is too difficult, right? You find all the derivatives up to and including the third derivative. You evaluate them at whatever this number here is, and then you plug it into that formula there. And then you try and make it as pretty as you can. That's as good as that's ever going to get. You do not need to FOIL anything out. That's not the way we do these things. Now, this function is not the entire Taylor series. Wouldn't the Taylor series be plus the next guy forever, right? So it's not a perfect match to sin x, but it will be, hopefully, a good match. Now, what would happen is that if you put this thing, which I'm not going to do because it would be messy and I'd probably hit the wrong button, but if you put this into the calculator and you put the original function sin x, they wouldn't be totally on top of each other, right? But they would be very close. And they tend to be really good at pi upon 4 and then getting a little bit less the further out you go. So this is the kind of thing you might get. Can you imagine that that's 1 cycle of sin x? Right? So there's 0, there's pi, and there's 2 pi. So that's what sin x looks like. Now, if I sketch this guy at pi upon 4, I guess I should do more of the sine function, right? Like this. If I sketched, if I put into my calculator this guy, what I would get is a really perfect fit here. And then it drift away, and then it get less accurate. Can you see it's a pretty good fit about here, and then it kind of drifts. Right. Now, if I did t not to the 4th, or t3 of x, I should say, not did t3 of x, which is this guy, but I did t of 3 million x. Imagine I just got a computer to do it, because no human being's going to do that. This fella and that one would look really, really good, maybe for 20 cycles, and then at the end, it'd start drifting. Can you see that they'd be more accurate for a longer chunk of time? And that's one of the properties of these Taylor's polynomials, is that they are really good close to the center value. What does that mean? Well, if I went and used this guy here, this polynomial, to find out what the sine of nothing 0.5 radians is, right? Then I would just plug 0.5 in here and I get an answer. It could be good to 4 or 5 decimal places. That's how close it would be, because it's like you know, about here, or actually it's more likely to be there, right? Really good. And so we know that from experience that this is a very powerful process. So if I didn't have a calculator, couldn't I, or a calculator that has sine button on it, couldn't I use this to approximate the value of a sine function? Let me try another one. This one, I'll do it in any pace. This one is going to be one of my favorite functions, and the reason I'm picking it is that it's dead easy to do, right? Because I just want to show you the process. Can you trust me on this one? That if I did t3 of x, right, for example, I would get 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. Can you just trust me if I went through all the derivatives and plugged in f dashed of 0, I'd get this. Now I'm just tidying up a little bit. Right, 3 factorial is 6, right? 1 times 2 times 3. So that's the guy. Now, I would like to know what the answer to e to the power of 0.012 is. Now I'm going to go to my calculator and tell you what the answer is. E to the power of 0.012 is about 1.012072289. Great, that's what it says. Now I'm going to use this fella, right, this polynomial, to estimate this guy. Would 2 decimal places be pretty impressive? Maybe 4, maybe 5. See what we get. We'll bend on it, so hopefully you can see it in the light. Here it goes. So it's going to be 1 plus 0.012 plus a half, which I'm just going to call 0.5, times 0.012 squared, plus a sixth, which I'm just going to do that way, times 0.012 cubed. And the answer I get is 1.012072288. 8 decimal places and darn close on the 9th one. Now, the reason why that is such an accurate answer is, isn't this number very close to 0? Right? 0.012 is very close to 0. And as long as you choose values of x close to where it's centered, the polynomial that you get, even t3 of x polynomial, will tend to give you very, very accurate answers, right? Almost exactly the right answer, right? Almost perfect. Now I'm going to do e to the power of 1. Now 1 is close to 0, right? But it's not bang on it, right? It's a fair distance away. So if I find e to the power of 1, it's 2.718281828. Now this guy was good to 8 decimal places. This fella here is much further away, right? 0 to 1, it's a noticeable difference. What kind of accuracy do you think I might get this time?
5 decimal places.
I don't know. It's as good a guess as any. Do you think it'll be? Do you think Sam's being generous? you think it might only be a couple? Do you think it actually might be more? It's kind of gut feeling. There's really no way of telling until we try it. So I'm going to use this fella at x equals 1. So it's going to be 1 plus x, which is 1, plus a half 1 squared, which is just a half, plus 1/6 of 1 cubed, which is really just a sixth. And the answer I get is 2.666667. Not very good. I'm not going to do the next one. But do you know if I did e to the 10, it would be hopelessly miles away. It wouldn't even be worth bothering to calculate. I know that the real answer to that and what this polynomial does are different. And if you think of it visually, what is happening is this is what e to the x looks like. And if you do the polynomial guy, you're probably getting a polynomial that looks something like this, right? A cubic. And can you see for this little piece of the world, the curve and the cubic are pretty good. But it doesn't take too long, right, before they separate, and they separate really badly. And by the time you did e to the 10, which would be over at the end of my table, the answer is like billions out, right? That's how bad it is. So the moral of this story is that a Taylor's polynomial like T3 of x is good as long as you pick close to the center, in this case 0, but gets worse the further away you go. So if you use an x value that's at 1, it's not great. At 10, it's useless. Is there any way I could improve the accuracy of my estimate polynomial?
Add more values.
That's it. So if you need the answer to 20 decimal places, and you need to be able to use it for quite big values of x, right? Ones that are far away from 0, won't you just do a T200 or a T2 million? Now, human beings can't do that, but can you imagine you can program a computer to do that relatively easily? Because doesn't a computer do a calculation in a microsecond? So a million of them wouldn't take any, would take a thousandth of a second. It would be instantaneous. And you could get whatever accuracy you like. So the last thing I want to do on how to find Taylor series is to show you a Taylor series where some of these terms are 0. So the one I'm sticking to is T3 of x. So it's going to be f of a plus f dashed of a, x minus a, for 1 factorial, second derivative over 2 factorial, and then the third derivative, that guy. Now, T3 of x basically says do a polynomial up to and including the third derivative. If the third derivative is 0 and that guy is 0, can you see that your answer might be made up of 2 terms? And one of them might just be x minus 1 squared. It's still called T3 of x because it was created using up to and including the third derivative, right? So I'm going to pick a nice easy function to show you the process. Suppose I wanted to do T3 of x sine x, and I'd like to center it at x equals pi, right? So that would be a equals pi. Then, well, let's do the working for it first. That's sine x. So at pi, it's the sine of pi, and the sine of pi is 0. That's fine. And then the derivative is cosine of x. And the first derivative at pi then becomes the cosine of pi, and that happens to be -1. Second derivative then becomes negative sine x. In this case, the second derivative at pi is negative the sine of pi, which basically means it's 0. And the third derivative is negative cosine of x. And the third derivative at pi is negative the cosine of pi, which is +1. So here's my T3 of x. Let's see what he looks like. He's going to be the value of the function at pi, the first derivative at pi, that guy, second derivative at pi, that guy, and the third derivative at pi, that guy. Now, this fella is 0, and this fella is 0. So basically, I won't bother writing them down. Would you agree 0 times all of this is still 0, so there's no point. So T3 of x in this particular case is going to be this guy, which is -1, x minus pi over 1, right, technically a 0 at the front, then a 0, and then this fella, which is 1 times x minus pi cubed over 3 factorial, which is 6. So what would it be called? X minus pi plus 1/6 x minus pi cubed. And we have now found T3 of x. Are we comfortable about this process? Find a function, find the first, second, third. If they wanted T4 of x, wouldn't you just do more derivatives? If they only wanted T2 of x, wouldn't you do fewer derivatives? And some, quite a lot of them, might be zeros, in which case those terms just disappear, right? In this particular one, I guess it was a bad choice in my part. Can you see that you've only got that guy? I'm not doing it now, but I bet you if I'd chosen cosine x as my original function, wouldn't I probably have ended up with these two would have been zeros, and I'd end up with a guy here and a guy here. So that's okay, right? T3 of x just means use up to and including the third derivative at a. Any questions about that? Okay, we're about to move on to our next phase then. It doesn't matter how ugly f of x is, because you're only using up to the third derivative, isn't it doable? You could differentiate 3 times. Might take you a bit of work, but you can do it. Okay, now the next fella is from your homework. Okay, I've lost you. There you are. And here we go. Question 1, I'm not even sure if it's really a question, but basically it's got little tabs on it and it helps you do things. So if I click on this one, it tells you what this module, this thing's going to do. If you hit in this one, it tells you a little bit more detail about errors, which we haven't really got into yet. And then we do this one, which is imported colon. Right. Here is a function. On this picture, just right now, just focus on the top picture. Forget about what that's about. We'll find out about that later. In this function, you have got the black guy is the f of x, and the red guy is what the Taylor's polynomial looks like. And up here, do you see this funny little slider? Right. If I do T2, can you see the red curve and the black curve don't really match much, but you see in that little middle chunk close to 0, aren't they pretty good? Now, if I up it to T4 of x, do you see it's better for longer. If I go to T12 of X, can you see here it's really good, drifts a little bit. Not so good on this side. You agree it's kind of got big issues on this side. But nonetheless, would you agree the red and the black curve are pretty close? And as long as I use values between what? Somewhere between -1 and 1, I should be able to get good answers. Remember we got a guy called interval of convergence. Remember that guy? The reason why you'll never get a perfect fit is that the interval of convergence for this particular function is -1 to 1. And so can you imagine that no matter what you do, you're always going to get a bit out, because if I tried to use it when x is 2, for instance, or God forbid, -2, do you see how bad it is? So one of the other restrictions on a Taylor's polynomial is that you should only use it for values of x inside the interval of convergence, right? So even if you did a t a million, which is great, but if you used it for a value of x that was outside the interval of convergence, it still would be a horrible approximation, right? It would look like this guy on the left. Okay, maybe you got lucky on the right, but can you see on the left, it's forget it, right? Cool. Now, if I move this little slider, what I'm doing here is changing the center. So if I do here, do you see how it's a really good fit at -1? Well, let's draw this back a little bit. There we go. Now I hit a little animate. Did you see that as the t, this is me animating the t here, right? Right now I'm centered at, looks like, yeah, I'm centered at -1, I'm pretty sure. There we go. This function centered at -1. It's not that great a fit, the red guy. See, as you add more, it gets better and better fit. If that animation could have continued, wouldn't that piece on the right-hand side bend in even better? Up to a point, and the point would be only do it inside the interval of convergence. That kind of cool thing, isn't it? So you can play about. Let's try another function. They've got some. There's my friend e to the x. Okay. Let's bring this guy back. That's not very good. There's a t2 of x. Now you see the red and the black are t4. Whoa, pretty good. t10. Can you actually tell the difference now? They're so close to each other. You know, remember the 8 decimal place kind of guys? That's the kind of accuracy you're getting. E to the x has an interval convergence of eternity, right? From -infinity to +infinity. So it's, you know, if you keep doing enough terms, you'll get a good fit. I think we did a sin x. Didn't we do a sin x? Yeah, we did the sin x. Let's wind this fella back. Right, here's a couple of cycles of sin x. There's t2, not great. t4, well, it's beginning to fit. Do you see it's beginning to fit at least these bends? If I go up to t8, better. If I go to 10, better. Finish on 12. Boom. Right, let's wind it back and do a quick animation. If you keep on adding terms, right, you do a t20x, a t40x, can you see that you're going to be a pretty good fit to the sine function for more and more of its life, right? Bigger values of x. I like this little program. Does it not show you, in one sense, that isn't a Taylor series really just another way of writing sin x? You know, an infinite Taylor series. That's quite insightful, I think. So let me close this guy off and return. Because now we're going to do the head scratching part. This is kind of the last bit. I believe when I did Taylor series way back on week 1, I said to you that most people who do Calc 3 will tell you that sequences in series is the hardest part, right? A lot of them find the stuff that's going to happen next easier. And that's my opinion as well, so hopefully. But we got one last guy. Obviously, you keep the best till last, right? So what is the best? How do you estimate the maximum error in using, say, a T3 of x as an approximation to some function f of x? So imagine I have a function, and I'm starting today with my easy one. When we do this tomorrow, we'll do uglier and uglier ones. We got this guy. And I've got, oh, actually, let's just do T2 of x, just so I don't have to write so much. Can you trust me that T2 of x, after a little bit of work, ends up being that guy, right? That seems reasonable. Now, let's suppose in this question that we're only going to use values, right? In the range -1 to 1. In these questions, that is typically part of the information. You're given a function, you're given a T2 or a T3 of x, or at least you find it. You're given an interval of x's, and then the kicker in the tail is, what's the maximum error in using, T2 of x to approximate e of x? Well, can you imagine that from -1 to 1, e of the x looks like that? And if I did T2 of x, can you imagine that it looks something like that? Now, what's the maximum error? Well, isn't the error the difference between what this function says and what the real answer is? It's basically that height, isn't it? So can you imagine if I plugged in -1, I might get quite a big difference between the answer, and this distance here is our error. But if I chose a value of x like here, wouldn't the error be tiny? If I used a value here, wouldn't the error be like 4 decimal places? Almost, almost no error at all. So we're not interested in a specific error, but what the maximum error would be. And we have a function called Rn of x. It's called the remainder function. I prefer the name that you might see, at least if you go to Scotland, you will, the error function. And it's described as that guy. Well, technically, we stick absolute values around them. We don't care if the error is because you're too big or because you were too small. Don't we only care how numerical it is? So the absolute value takes care of that, right? So this is your error function. And if you think about it, it makes sense. Isn't the error the difference between what the function says it is and what Tn of x is? So if I wanted to find, R3 of x, wouldn't it be f of x take away T3 of X. Does that make sense? Now, you could actually do this by evaluating this, evaluating that, and subtracting them, but we use this instead. The remainder, right, function, R3 of X, it's this guy. Do you recognize who this guy is? Isn't he the next term that you didn't use? He's the next term, right? That's what the guy that would go here would be, right? The closest analogy I've got, can you remember doing alternating series? If you used the first 5 terms, wasn't the error the 6th term, the one you didn't use? Right. So how do we use that? Well, I just need to find the maximum value of the 4th derivative of A, the maximum value of x minus a to the 4, and then I can calculate this guy. Okay. So in this question here, I've just actually realized I'd made it a 2, so let's be consistent. Okay. Wish I hadn't done that, because now I have to go through all of this. So I need to calculate the 3rd derivative of a, x minus a power of 3 over 3 factorial. For my function f of x, isn't the 3rd derivative e to the x? Great. Now, centered at 0, which I should have told you, this fella, right, is e to the x. What's the maximum value when x is numbers -1 to 1? What's the biggest answer that e to the x will be if you use values of x in this range?
E.
Agreed. E to the power of 1, e. So that's one of my answers taken care of. Right. I have technically x minus 0. I have x cubed, right? That's what this guy is. What's the maximum value of x cubed when x is used in this range?
1.
I now have all the pieces. The 3rd derivative, the biggest value it's going to be is e. This guy is 1, and this guy is, so there's your answer. The maximum error that you would get using this polynomial to represent e to the x is e over 6, right? Which is about a third, I think. E divided by 6. It's about 0.4531, which is, by the way, why, remember I did e to the 1 and it was horrible? It could have been as bad as 0.45 out. Which means we now have a way of estimating what the worst case scenario is. Oh, I've got this ugly function, and I'm going to use T5 of x to approximate it. and I'm only going to use values of x between negative pi and pi. What's the worst case scenario? What's the worst error I would get? And that's what we're calculating here, the maximum error. And now, if the maximum error ends up being 0.00002, aren't I going to be really happy and say, I can use my Taylor's guy and he's going to be good to 5 decimal places? But if the maximum error is 42, you really don't want to use it, do you? I mean, if my answer could be plus or minus 42, wouldn't it be better just guessing? I might be closer. So do not do the slight slag against engineers.
Did you plug in 1 for A?
Did I
I'm
plug in
confused.
1 for A? No, technically, f dash of A is a placeholder. It just means the maximum value of f triple dashed of x in the range -1 to 1. So I really just called it f triple dashed of A. It's actually the largest value where A is between -1 and 1. So think of what's the biggest value the triple derivative would be in this range. And that's what goes here. And the biggest value of that in that range goes here, and it's over that number at the bottom. Oh, back to my insult on engineers. An engineer was being asked what 1 plus 1 is. And he said 2. And they asked him if he's sure. And he said 2 plus or minus 1. And then a second one, which was a Polish engineer, was asked the same question. And he was asked, what's 1 plus 1? And he said 2 plus or minus infinity. Because technically, isn't the answer to every numerical question in the universe 2 plus or minus infinity? So what's the moral of that story? If your tolerance, which is what we call the error, right? If your tolerance is too big, aren't you in trouble? The bridge will fall down, the building will collapse, the submarine will sink when it's not meant to. Bad things will happen. So we do like to use Taylor's polynomials, but isn't it a good idea to know how accurate they are when we're using them? Okay, say hi everybody. And